हेलो बच्चों, this is the video number 7 of the unit Electrostatics. In this, we will study about the applications of Gauss theorem, as we have studied about Gauss theorem in previous lecture. Under this topic, we will study three applications of Gauss theorem. First is electric field intensity due to infinitely long straight uniformly charged wire. Second is electric field intensity due to uniformly charged infinite plane sheet. And last is electric field intensity due to uniformly charged thin spherical shell. In today's lecture, we will study only first two applications, and the last application we will study in the next video lecture. So the first topic is electric field intensity due to infinitely long straight uniformly charged wire. Here the sense of infinitely long straight wire doesn't means the length of the wire is infinite, but the distance of the point of observation at which we are going to find out the electric field is very small in comparison to the length of the wire, so that we can consider the length of the wire as infinite. Now to find out the electric field intensity at a point near the wire, let us consider a wire xy of infinite length having a linear charge density lambda, and P is the point of observation at which we are going to find out the electric field intensity at a distance r from the wire. E is the electric field intensity of linear charge distribution over the length of the wire, and the direction is outwards. Here we are going to draw a Gaussian surface passing through the point P around the wire. So the shape of the Gaussian surface is cylindrical here. Here L is the length of the Gaussian surface as shown in figure, and we have considered a small area element dA at the two surfaces of the Gaussian surface. First surface is the curved surface of the cylinder, and second is the flat surface of the cylinder. dA is the area vector of the small area element dA as shown in figure. At the curved surface of the cylindrical Gaussian surface, the angle between electric field intensity and the area vector is 0 degree, and at the flat surface of the cylindrical Gaussian surface, the angle between electric field intensity and area vector is 90 degree as shown in figure. So total electric flux through the Gaussian surface can be written as phi is equal to closed integral E dot dA. Here in the diagram, at the curved surface of the Gaussian surface, the angle between electric field intensity and the area vector is equal to 0, but at the flat surface of the Gaussian surface, the angle between electric field intensity and the area vector is 90 degree. Therefore, we will get the value of flux through the curved surface only, because cos 0 degree has value 1, but cos 90 degree is equal to 0. Therefore, flux through the flat surface of the Gaussian surface will be equal to 0. Therefore, we can write flux phi is equal to closed integral over the surface of E dA cos 0 degree, which is again equal to E closed integral over the surface dA. Here, since the radius of the cylinder is constant around the wire, that is R is not changing. Therefore, the electric field will be constant around the wire at every point at a distance R. So, integration of surface area will give the value 2 pi RL. As we know that the curved surface area of a cylinder is 2 pi RH. Here R is the radius and H is the height of the cylinder. So in the diagram, the radius of the cylinder is R and the height is L. Therefore, the area of the curved surface of the Gaussian surface is equal to 2 pi RL. Now, after integrating the closed integral over the whole surface of the Gaussian surface, we get the value of flux phi is equal to E into 2 pi RL. Now we know that as Q is equal to lambda into L, which is charge, total charge on the linear charge distribution of the wire, where lambda is the linear charge density and L is the length of the wire, and flux phi is equal to Q by epsilon naught according to Gauss theorem. So we can put the value of Q in this equation. We get phi is equal to lambda L by epsilon naught. By putting the value of phi from equation 2 in equation 1, we get the expression of electric field E is equal to lambda by 2 pi epsilon naught R. Here we can see that electric field intensity is inversely proportional to R. Therefore, the variation of electric field occur according to this relation. And electric field intensity is directly proportional to lambda. So, for lambda is greater than 0, that is, when the charge distribution will be positive or charge density will be positive, the direction of electric field will be outward. And when lambda will be less than 0, that is, when the charge density will be negative, the direction of electric field will be inwards. The next application of Gauss theorem is electric field intensity due to uniformly charged infinite plane sheet. Here the sense of infinite plane sheet is that the point of observation at which we are going to find out the electric field intensity is very close in comparison to the area of the sheet, so that we can consider the area of the sheet as infinite. Now to find out the electric field intensity at a point near the surface of the plane sheet, let us consider a thin non-conducting infinite plane sheet of charge having surface charge density sigma. P is a point at a distance r from the sheet at which we are going to find out the electric field intensity. E is the electric field intensity. The direction is outwards, and now we are going to draw the Gaussian surface around the sheet as shown in figure. The Gaussian surface is drawn at a distance r containing the point P, and the shape of the Gaussian surface is cylindrical. It can also be a parallelopiped, as there is no effect of the shape of the Gaussian surface. I have explained you earlier in the previous lecture. So we have taken 2 points near the thin sheet at the same distance, which is P and P dash. dA is the area vector of small area element dA containing the point P and P dash on both sides of sheet. As we know that on the curved surface, the angle between electric field intensity and the area vector of the Gaussian surface is equal to 90 degree. Therefore, the flux through the curved surface of the cylinder will be equal to 0. That is, the flux through the cylindrical Gaussian surface will be equal to 0. So, we will have to find out the flux through the cross-sectional area A only. Now, the total flux phi through each end of the Gaussian surface is given by phi is equal to 2 times closed integral E dot dA, as the magnitude will be same on the both sides of the Gaussian surface. Therefore, we get phi is equal to 2 into E into A, as when we take the closed surface integral of dA, the value of this we will get A, because the total area is A we have considered before. As we know that Q is equal to sigma into A, where sigma is the charge distribution on the sheet, and using the Gauss theorem we can write flux through the Gaussian surface is equal to Q by epsilon naught. By putting the value of Q in this equation, we get phi is equal to sigma into A upon epsilon naught. By putting the value from equation 2 in equation 1, we get sigma A upon epsilon naught is equal to 2 into EA. By doing cross multiply, we get the final expression of electric field intensity at a point near the plane sheet. E is equal to sigma by 2 epsilon naught. We can see from this equation that the electric field intensity is not depending on R. Therefore, it doesn't matter that where is the position of the point of observation, because at all the points around the plane sheet, electric field will be same. Homework: revise the continuous charge distribution topic and learn the formula of charge density in all the three cases. Learn the derivation and expression of electric field intensity of both the derivation which I have explained in this lecture. And last is study the application of Gauss theorem, which is the electric field intensity due to two thin infinite parallel sheet of charge. Thank you.